Welcome back, everyone, to week 2 of our Science 102 course. And this week we're going to be talking about maps and GIS. So what we're really doing with this lesson is laying some of the groundwork that will help us in future lessons, because maps and GIS are some of the most important tools that earth scientists use. So we're going to be making use of a lot of maps and GIS throughout this course. So I want to take some time to really dig into what these things are and how you use them so that we can then apply those skills as we go through the later lessons of our course. So our goals for this lecture are first for you to be able to explain the functions of spatial data, to locate places using latitude and longitude, to read some of the major types of maps that are used by earth scientists, and then to use some of the basic functions of geographic information systems, which is what GIS stands for. So as I said, maps are one of our most important tools as earth scientists, because in order to understand what is happening on the earth, we need to know where it's happening. So that where is what brings us into the realm of maps and GIS. So if we have data that includes the where, the data that tells you where the things being described are located on the Earth, we're dealing with spatial data. So spatial is the adjective form of space. So if something's located in geographical space, it is spatial data. And if we have spatial data, we can make a map. So a map is showing us some of our spatial data. And it's a simplified representation of the surface of the Earth, which we've made for some particular purpose. So we have a purpose in mind, and based on that purpose, we choose how to simplify what's going on the surface of the Earth to create a map. So I've got an example map here on the slide. This is titled The Physiographic Provinces of Pennsylvania. So this is basically the landforms that we see across the state of Pennsylvania. So this is based on spatial data. We have data about what kinds of landforms are found in each of the different parts of the state. And we can make a map out of that. So we can look at that map and we can either look for a certain landform and see where that's found, or we can look at a certain place and see what kind of landforms are in that place. And this map is a simplification, of course. There's lots of things in the state of Pennsylvania that are not on this map, right? You can see that we've got the outlines of the counties there, but we don't have, say, the outlines of cities and towns. We've got some of the rivers indicated, but that is certainly not all of the rivers there are. And those areas of different landforms are kind of simplified. So it's not as if you get to that line and you very suddenly change from the high plateau to the Pittsburgh low plateau, by taking one step forward. They've simplified it and made it into these two distinct blocks of color to make it easier for us to understand, because the purpose of this map is to communicate to us a general idea of what kind of landforms are found in what parts of the state. Okay, so a map is simplifying the Earth to serve some sort of purpose. We have a goal for it, and we're using it as a tool for something. And so because of that, every map is going to be selective in what it shows and how it shows it. So some questions that are important for you to ask about any map, and so that's going to include the maps that we look at in this course. It should include any other maps that you run into any other time in your life, is you should ask first, when and how was the data for the map collected? So something like that landforms map on the previous slide, the when might not be as important because those landforms don't change a lot. For other things, they may change very quickly. So a map based on the 2020 census might look very different from a map based on the 2010 census, because the kind of things that the census is asking about, populations and stuff, can change a lot over the course of 10 years. And so it's important, if you see a map, to know when that data was collected and also to know how it was collected. So a map that's based on the census that asks questions of every single person in the entire country is going to be different than a map that was based on, say, a telephone survey where they contacted just a sample of people and made a map based on those answers. Or a map that's just kind of based on vibes, on somebody's impressions of different areas without actually collecting any quantitative data. So you want to ask when and how was the data for this map collected. And if you can't find that out, if the map isn't giving you that information, it's not pointing you to the source for that data, then you should be really suspicious. You should be really suspicious that the map can't tell you its sources and how it got that data, because that probably means it's not from a good, reliable source, and they're trying to hide that from you. Second, you should ask what symbols were chosen to represent the data. So in the map that we just saw, the symbols that were chosen were big areas of block color. Right, so they chose those symbols to represent the data. Other sorts of maps may use textures. They may use little icons to represent things. So you want to look at what kind of symbols are being used and whether they're appropriate symbols. Maybe they're misleading symbols in some way. So you want to look at the symbology, and then you also want to ask what projection was used to turn the round Earth into a flat map. And so we could spend an entire lesson talking about projections, and I do that in some of my geography courses, but I want to give you just a very brief one slide about projections, just so that you're familiar with the concept, so that as it comes up later, we can, we're talking about the same thing. So a projection is the way that we take the round Earth and put it on a flat piece of paper. And the larger the area your map is trying to cover, the more important it is to think about projections. Because if we have a map of like just the town of Slippery Rock, the differences between projections over that small of an area really aren't going to make much difference at all. And because, at that scale, the Earth is so close to being flat, because, it's so big, so a little tiny piece of it is so close to flat. How you go about taking this very slightly rounded area and flattening it out doesn't make as big of a difference. But if you're looking at the entire world, right, we've got a globe, and you're trying to flatten that out into a flat sheet of paper or a flat screen, since most of the maps we're looking at are actually going to be on a screen rather than physically on paper. If you're going to flatten out the entire Earth, you're going to inevitably introduce distortions of one sort or another. So you're going to want to pick the projection that's appropriate to what you're doing. Which kind of distortions are acceptable and which aren't for the purpose that you have for your map. So I've got just 3 examples here. So the one on the left, it's a projection you may have heard of. It's called the Mercator projection. And the Mercator projection keeps all of the directions correct. So you can draw a line on a Mercator projection, measure the angle of that line, follow that angle on a compass, and you'll walk exactly on that line and get to your destination. So the Mercator map was invented for sailing ships back in the days when they would plot out on a paper map with a compass where they're trying to sail to. So that was extremely useful for them. That map preserves the directions, but it changes the areas of things. In order to preserve the directions, it has to distort the areas. So on the Mercator projection, things get disproportionately large as you get towards the poles. And you can see that with all those little red circles on the map. So those circles are all equally sized circles on the globe. If we had a globe based on that map, those circles would all be the exact same size on the globe. So then you can see when they're put on the projection, they get bigger as you get farther from the equator. That the sizes of things are getting distorted to be larger farther from the equator. But they all stay perfect circles. Right? Directions are kept accurate, so the shape of the circle doesn't change. It just gets bigger in some areas. Then in the upper right, we have an example of what we call an equal area map, where we keep the areas correct. But in order to do that, we have to distort the directions. So this particular one is called the Moloide projection. You don't need to know the names of these projections for this class. You just need to kind of grasp the concept that each projection does some things good at the expense of other things. And so if you look at those red circles on the Moloide map, you'll see that they remain the same size. So they're the same size on the globe. They stay the same size on the projected map. Areas are kept correct in proportion to each other. On the other hand, you'll see that those circles, they look pretty circular along the equator, but they get really squished as you get towards the poles and especially towards the outside edges of the map. So the directions are getting all screwed up in order to keep the areas correct. You can't have both of those things at the same time. You got to choose which one is appropriate for the map that you're making. And then the third example there is what's called an orthographic projection. That is essentially the take a photo of a globe projection. The orthographic projection is what you get if you just took a photo of a globe, and that projection distorts both areas and directions. So you can see that the circles near the center stay nice and round, but as they get towards the edges of that map, they get smaller and they get extremely squished. So it looks cool, and there are appropriate uses for an orthographic projection, but it's distorting both directions and areas. So the point of all this is that you should pay attention to what projection is being used for a map, especially if it's a map on a sort of continental or global scale, because sometimes they've chosen a projection that will maintain direction, sometimes one that will maintain area, sometimes one that has another positive feature to it. But in doing that, there's always something that is lost. There's always something that's distorted in order to do the thing that you're trying to do correctly. And you want to pick the right projection for the right map. If you're trying to sail your ship across the ocean, you probably want to use a Mercator projection rather than a Moloide. But if you're trying to, say, make a map of deforestation so we can see how much area of forest has been lost over some period of time, you probably want to use the Moloide because you're interested in the areas of forest and not so much what direction you'd sail to get to those forests. Okay, so latitude and longitude is our system for locating things on the Earth. So if we want to know where something is, we need to know its latitude and longitude. And these are based on the fact that the Earth is almost a perfect sphere. So we often talk about the Earth being a sphere as kind of an easy shorthand, but it's not quite exactly a perfect sphere. It's actually what we call an oblate spheroid, which means that it's slightly flattened at the top and bottom and slightly bulges around the equator due to the way it spins on its axis. It kind of bulges out at the equator and squeezes in a little bit at the poles. It's enough to create headaches for people doing a really high-end GIS kind of work where you have to deal with how to account for those kinds of things on the Earth, but it's not enough that if you look at, say, a picture of Earth from space, that you can really see that difference with your eyes. So we've got this Earth that is almost a perfect sphere, and it's spinning on its axis. So we have this imaginary line going through the center of the Earth around which it spins, and North and South Pole are where that axis touches the surface of the Earth, right? So if you were standing exactly at the North or South Pole, you'd be spinning in a circle. So that axis provides a reference point for location on the Earth. And we specify that location in degrees of latitude and longitude. So this is in degrees, and you probably remember from your geometry classes, a circle is 360 degrees to go all the way around. But we don't use all 360 in explaining the locations of places. So for latitude, we're talking about our distance north and south of the equator. So we've got our axis with the North and South Pole. Then the point around the middle, halfway in between, is the equator. That's a circle that goes around the center of the Earth, halfway between the poles. The equator is designated as 0 degrees latitude. And so then if you were to travel from the equator up to one of the poles, you'd be going a quarter of a way around the Earth. Right? The distance from that middle point to the top or to the bottom is a quarter of the way. That's 90 degrees. So our latitudes are always somewhere between 0, which would be the equator, and either 90 north, which is the North Pole, or 90 south, which is the South Pole. Okay, so the latitude is always in degrees between 0 and 90, and unless you're at 0 at the equator, then you need to indicate, is it north or south? Okay, which hemisphere are you going into? Then to designate distances east and west, we use longitude. Right, so latitude is north and south of the equator. Longitude goes east and west. But here, we don't have a natural reference point the way we do for latitude. Right? We have a north and south pole. We don't have an east and west pole. So we have to arbitrarily designate a starting point for our longitude. And so that has been arbitrarily, or really based on a whole lot of politics that happened in the 1800s that we won't get into in this course, has been designated as what's called the prime meridian, which runs through the observatory in Greenwich, England, which is just outside downtown London. So we've designated that spot as 0 degrees longitude. And so just like the equator, it's not 0 isn't an east or west, it's just 0. But then you can go east and west from that prime meridian all the way around to the other side of the Earth. And so going halfway around the circle, that's 180 degrees. So we have 180 degrees on the opposite side of the Earth from the 0. And then everything in between is some number of degrees between 0 and 180, east or west. Okay, so you're 0 to 90 north or south, and then 0 to 180 east and west. If you give a north or south coordinate and an east or west coordinate, you've now given us your latitude and longitude. Now, just as sort of a fun question, do you want to take a guess what the latitude and longitude of Slippery Rock are? So you can pause this if you want to take a minute and try to guess the latitude and longitude of Slippery Rock. So I will now tell you Slippery Rock is about 41 degrees north. So we are just under halfway from the equator to the North Pole. We're actually angle-wise slightly closer to the equator, right? Because 45 would be halfway. And then longitude, we are at about 80 degrees longitude. So not quite halfway from the prime meridian around to 180. So that is our approximate latitude and longitude. Okay, so we have a system for describing where things are on the Earth. So we can then associate those coordinates with data about what's happening at that location, and that gives us spatial data. So there are a couple of different ways that we can collect spatial data. So one of those ways is a field survey. So we can actually go out into the field. We can go to the place and we can make our observations of whatever sort, bring whatever instruments. Maybe we're measuring the temperature. Maybe we are examining what kind of rocks are at that location. Whatever data it is we're gathering about that location. We actually go out into the field, we gather that piece of data, and then we connect that data to spatial coordinates. And these days, the main way that you would do that is using GPS, the Global Positioning System. In the past, a lot of spatial data might be collected using various types of surveying and triangulation and stuff. I'm just not even going to get into all that in this lesson because far and away, the main way that the spatial coordinates are attached to data in a field survey context these days is with GPS. So GPS is a system of satellites that are orbiting around the Earth. And by receiving messages from those satellites, you can determine exactly where you are on the surface of the Earth. And so this is a system that was initially developed by the US military, but then starting in May of the year 2000, it was made available for civilian use as well. So it used to be the military would scramble the signal so that you couldn't get reliable GPS signal because they were worried about like national security issues. But then they realized that it could be incredibly useful for both regular people and for a lot of companies to be able to locate things that accurately. So they made it available for civilian use since 2000. So basically what's happening is the satellites are orbiting the Earth and they're sending out messages with exact times. So they will send out a signal that says, hey, when this signal is being sent out, it is exactly such and such time. It is exactly 1:35 and 23.607 seconds, whatever the time is. It's sending out that signal. Then your GPS receiver, which could be a dedicated GPS device, or these days, you have a pretty good GPS receiver just in your smartphone. So your phone has a clock on it that is synced exactly with the clocks on these satellites. So when your phone receives this signal, it compares the time in the signal to the time that it was received. It will be received some tiny little bit of time later than when the signal was sent out. Then your phone also knows exactly where those satellites are supposed to be in their orbits around the Earth. They're making very predictable orbits around the Earth. And so then your phone can say, aha, this satellite would have been at this exact position when it sent this signal out, and it took this amount of time for the signal to reach me, and I know those signals should be moving at the speed of light. So we're going to talk in our next lesson about electromagnetic radiation and the speed of light, but there's a predictable speed that we would expect those signals to travel. So if we know how long it's taken the signal to get there, we know where that satellite is, we can calculate how far you are away from that satellite. If you do that with several satellites, you need a minimum of 3, just geometrically, to isolate a single point. You need the distances from 3 of these satellites. Usually to improve accuracy, they try to look at more than just 3 satellites. You usually have more than that sending signals that your phone is receiving at any one time. But you can use those distances to figure out where on the surface of the Earth you actually are. So you're calculating your distance from these satellites based on the time lag of these signals coming to your phone or your other GPS receiver. That gives you your latitude and longitude coordinates, and then when you have those coordinates, you associate them with whatever other data you have about the place you are, right? The temperature there, the rock type there, whatever it is you're gathering data about. So that's one way that we can collect spatial data. Another important way that we collect spatial data is through remote sensing. So remote sensing, as the name implies, is sensing things from remotely, far away. So you have some sort of a vehicle that flies above the Earth. And so this could be an airplane, this could be a drone, and this could be a satellite. And you've seen on the first slide of my lessons, I've been using some cool satellite photos there. So that's a major source of spatial data via remote sensing. So you have some sort of a vehicle flying above the Earth, and it's got a sensor on it. And the sensor senses what's going on the surface of the Earth below it as it passes over. And so these sensors could be passive, which means they collect existing radiation and signals. So for example, if it is a sensor that's sensing visible light, okay, so it's flying over the Earth during the day, there's sunlight reflecting off the Earth, and it's just going to sense that it's basically working like your standard camera, right? It's just picking up the light that's bouncing off the Earth and recording that. Could also be recording wavelengths that we can't see. It might be recording, infrared radiation or ultraviolet radiation that's bouncing off the Earth, just passively collecting what's out there. Or it could be an active sensor where it emits radiation and bounces that radiation off the Earth in order to record what happens. So that, as an example of that, we have what's called LiDAR, which is a laser-based system that can be used to get really highly accurate measurements of elevations and the shapes of things on the Earth's surface at a really close resolution. And there, rather than just picking up the radiation that's already bouncing off the Earth, it's shooting out its own laser and then seeing what happens, how long it takes the laser to bounce back to it. So in either case, we are remotely sensing, we're looking from a distance away at what's going on the Earth, and we collect that information, and we know where our vehicle was as it passed over, so we can attach that spatial information to the data that has been collected. So we've got this spatial data, and we want to make a map of it so that we can see what's going on. So I want to go through a few of the common types of maps that you're going to encounter in this class. So the simplest kind of map that we might have is a map of point data. So this is a map where we have observations of things, whatever it is we're making a map of. We've got observations of where they happened, and so we put some sort of an icon on the map that indicates what was going on there. And we can vary the color, size, shape of these icons to indicate other information about it. So as an example, I've got a map here of earthquakes in the United States. So what you see here is anywhere there was an earthquake, they're going to put an icon on the map. And the little legend that you see there shows how they're using color, shape, and size to tell you things about those earthquakes. So the size of the little circle shows the magnitude, how big of an earthquake it was. The day that I took this screenshot, we did not have any big earthquakes in the United States, so all the ones on the map are really small, but if there was a big one, it would show up bigger. Then the color is showing you how long ago that earthquake was detected. as of the time that I took this screenshot. So you can see we have several earthquakes there in kind of the middle of the United States that are in orange that show that those observations are a day old. So there's been an earthquake within the past day in those locations. I don't see any on there that are red, which means they were detected within the last hour. So there have been no earthquakes in the last hour at the time that I took this screenshot. So the color is telling you something about when that earthquake happened, and then you can see the shape. A circle shows that it is an actual earthquake. A diamond would show you that they detected something that had a seismic waves, that shook the earth that was not actually an earthquake. Some other kind of thing happened, maybe a gigantic landslide that made the earth shake. That's not an earthquake, so they would mark that differently. Doesn't look like we had any of these non-earthquake events at the time that this map is indicating. And so you can see some of those things that I said that you should think about when you look at a map, including things like how the symbols are being used. Right? They've made, I think, a pretty good choice of symbols here, that bigger earthquakes are bigger symbols. That's nice and intuitive, easy to understand. It's not going to confuse you or mislead you. All right, the map would still technically be accurate if they used big circles for small earthquakes and small circles for big earthquakes, but it would be confusing. You'd have to keep reminding yourself as you looked at the map. So it wouldn't make a very good communication of that information. Same thing with the age, right? The color gets faded the older that it is, right? The red really stands out for the really recent ones, and then it fades down to an orange, yellow, white as you get to the older ones. That, again, that's a good symbology. That makes sense because the red ones are going to stand out the most. Those are going to be the most recent events on the map. So that's a point data map. Probably the easiest, the most straightforward to read. Another type of map you may encounter is called a choropleth map. So with a choropleth map, we take our area that we're mapping and we divide it into some sort of area units. So in the example map I've got here from the US Census, the area units are counties. So the map is divided up into all the counties, but those area units could be anything. Right? They could be zip codes, they could be watersheds, they could be planning districts, they could be, whatever kind of areas that are suitable to the data that you have. A lot of times you only have data that's aggregated, say, at the zip code level, so that's what your area units have to be. But other times you can break it down more, you could do smaller area units, you could aggregate it into bigger ones, whatever. But you're breaking your map up into these area units, and each one is colored to show its value on whatever variable you are mapping. So our spatial data here is about persons per square mile. So this is population density. So you've got the legend there that shows what the different colors mean. So the darker bluer colors are more dense, the lighter greener and into kind of yellowish colors are less dense areas. And so each county is colored in a solid color based on the average population density across that whole county. And as you look at this map, probably makes a lot of sense to you if you're familiar with the state of Pennsylvania, right? You see Allegheny County, where Pittsburgh's located, standing out as more dense than the things around it. Then you get into the north central part of the state. If you know about that area, there's very few people up there, so it's very low population density. And then you've got more high population density around Philadelphia in the southeast, right? But it is done by area unit. Each county, in this case, is one data point, right? We have the data for what is the average population density in X county. We represent that with the color on the map. Another type of map that you'll run into is a raster. So with a raster, rather than dividing the map up into these area units that are based on like political boundaries or something like that, you're dividing it up into equally sized pixels. So all these little squares. And so you're probably familiar with that. If you've ever taken a digital image and zoomed way in on it, you can see all the little pixels because your standard digital images are in raster format. So raster is a format that's used for spatial data. It's also used for just like the photos out of your camera. And so I've got there on the screen a super zoomed in bit of that Landsat image that was on the first slide of this presentation. So that was a satellite image of the Quabbin Reservoir in Massachusetts, and that is in the form of raster data. So if we zoom in really far on that that image, you see the pixels. So each pixel is showing you, in this case, what the color of the land was within that area of the land. So you've got a wide range of different colors. It's recording whatever is being shown there. You could also take that complicated raster data and you could simplify it. So, looking at that image there, you can see, okay, some of those areas are clearly land, some are clearly water parts of that reservoir. So we could take that and go from each pixel showing some color that was the color of the land there and say, well, if it's a greener color, we're going to just call it land. If it's a bluer or blacker color, we're going to call it water. And so we can kind of turn it into this binary thing, land versus water. And that's what I've done in the second picture there. You can see it's the same area, but I've just turned it into, I've simplified the data into land versus water instead of showing you all the different variations of color that were there when the satellite went over and took that image. But it's the basic idea is for every pixel, every little square on this data set, you've got its value on the variable that we're mapping, either the variable of color of the land in the first one or the variable of is it land or water in the second one. Okay, then another important type of map that we'll be looking at is called an isoline map. And so isoline maps are very important when we're dealing with variables that change gradually over space. So if you think back to the population density, right, that could change very suddenly. You could have a very dense area, and then, on the other side of the railroad tracks, there's nobody for whatever, there's many reasons that might happen, right? That might change very suddenly. But some things change gradually over space. So these are things like elevation, right? You occasionally get like a big cliff or something, but most of the time, right, the land goes up gradually and down gradually. Or as we see in the example image here, air pressure. So our air pressure, we don't get a sudden change of pressure from high to low pressure. We have a high pressure here, we have low pressure there, and it changes gradually in between them. So isoline maps are really good for showing variables that change gradually over space. And you can take a small number of observations, small number of actual measurements, and then draw isolines to help us see what's going on across the whole area, not just where you have those specific measurements. So what's happening here on this map is each line, and we're focusing on the black lines on this map, kind of ignore the colored parts, that's showing rainfall areas, which is, showing a whole other thing there. But if you focus on the black lines, those are isolines showing atmospheric pressure. And so along each of those lines, you have the same pressure. So each of those lines is a line of equal atmospheric pressure. So if you look, for example, in kind of the middle of the country, you can see that line that runs around, there's 3 H's for high pressure centers there. It kind of runs around them through like Nebraska, South Dakota, Iowa, Kansas. That line, you'll see there's a number right on it, 1016. So that is the value along that line. That is in millibars. That's a unit we use for measuring atmospheric pressure. So if you were to follow exactly along that line, the air pressure would stay exactly the same. You would be at exactly 1016 millibars all the way around that line. If you left that line and went in either direction from it, then the atmospheric pressure would go up or down. So if you went into the center of that loop that's making, you can see there's the H's there. There's also a few higher values. You can see there's a 1019 there in South Dakota, for example. So you'd be getting higher pressure as you moved into the interior of that little loop that's made. But then if you go the other direction, you'd see you're going towards some of those L's. So for example, if you headed northeast from there across kind of Minnesota into Canada, you're heading towards that L. The air pressure is getting lower as you're going towards the L. And as you cross other lines, that gives you an indication of exactly how much lower the air pressure has gotten at each of those steps along the way. So the lines connect places of equal value on your variable, which in this case is atmospheric pressure. And so if you are moving from one line to the next, you're changing on that variable. So this is an example of isolines for atmospheric pressure. An extremely common type of isoline map that we're going to be looking at, and which I want to spend a little bit of time on now because it's very important for our class. You're going to use this a lot, that you're able to make sense of a topographic map. So a topographic map is a subtype of isoline map in which the lines are connecting points of equal elevation. Right? So our variable that we're mapping is elevation. How high is something above sea level? And we can draw isolines for that because, as I said, elevation tends to change gradually over space. You go up the slope and down the slope. You have relatively few sudden cliffs where you got a big jump from a high elevation to a low elevation or vice versa. So what we're doing is we're essentially translating the three-dimensional landscape into a two-dimensional map. And so one way that you might think of it, to kind of conceptualize what these lines are doing, is imagine that our landscape is being flooded and the water level is slowly rising. Right? So that water level is going to be the same, right? Water evens out at the top. So the water level is going to be the same elevation everywhere. And so that water level will rise. It'll rise, say you raise the water level 10 feet. Some things are going to get drowned under that water. Other things are still going to be above water, and you're going to have the kind of the shoreline, the edge of how far up the water goes. That shoreline is, you could draw that on a map as an isoline that is 10 feet above the previous water level. And if you raise the water level another 10 feet, that new shoreline that you've created, right? It's the same elevation all around because the water is flat. That new shoreline, you could draw that on the map as an isoline that's another 10 feet above the previous one, 20 total feet above the original water level. You could keep doing that, gradually flood your landscape and draw those coastlines as you go, and you would get isolines that would show that elevation. And so in this example, we're raising the water level by equal increments. So on topographic map, our isolines are always equal increments of elevation. Exactly how big those increments are depends on the map. So it's a thing you should always check out when you encounter a topographic map, is what is the elevation difference going from one line to the next, because some maps will do 10 feet, some will do 20 feet, some will be in meters instead of feet. This is one case I mentioned, or that we were going to use mostly metric units, SI units in this class. But for various historical and political reasons, a lot of topographic maps are still made using imperial units, using things like feet. So you will see feet being used in some topographic maps, as well as meters and others, which is why you always need to check what units it's being used in. So if you're making a topographic map like this, you're drawing these lines of constant elevation. You'll find that sometimes they're closely squished together, other times they're spaced wider apart. And that's going to show you how steep the slope is at that location. So if you have very closely spaced lines, what that means is over a certain horizontal distance, you're going up or down by a lot of units of elevation. Whatever, if we're saying each isoline is 10 feet of elevation in difference. If you go a certain distance forward and you've crossed 3 of those lines, you've gone up or down 30 feet. But if in another part of the map, you go forward that same distance and you only cross 1 line, you've now only gone up or down 10 feet. So that's a much shallower slope. So when the lines are closely spaced together, you're going up or down a lot of elevation in a short horizontal distance. That's a steep slope. If the lines are very spaced out, so you have to go a long horizontal distance in order to go up or down very much in elevation, then you've got a gradual slope. So let's take a look at an example topo map. So this map is from the United States Geological Survey. This is the style of topo map that'll be the most common one that we'll be looking at, because we'll be looking at a lot of stuff about the United States, and USGS has made these topo maps of the entire country. They update them regularly, so they're a really good resource to look at. So it's a good thing for you to be able to read them, to look at it and understand what's going on. So when you look at a map like this, the first thing you should do is just kind of get yourself oriented. Get a sense of what's going on here. Where are the hills? Where are the valleys? Etc. So in order to do that, there are a few things that you can look at. So one thing to keep in mind is that generally speaking, you'll find the topographic lines making little rings around hills. So hills tend to be, have kind of a peak to them, and the lines make kind of rings around that hill going down from the top of it, whereas valleys tend to be the crevices in between the hills. Right? So you tend not to get, this like bowl-shaped valley that's going to have topographic contour lines as like a little ring around those. The valleys kind of form the cracks in between the hills. So when you see little rings, you're probably at the top of a hill. So if you look at pointer A there, you can see that little ring there, and then there's another kind of ring around that, another one around that, and the farther out you go, the harder it is to see the rings. They get kind of funny shaped and merge with other ones. But starting from the top, you can see a few rings there. So that's a good indication. That's probably the top of a hill. And in this case, you've got that road, Dieters Hill Road, right next to it that gives you an extra hint that you've got a hill there. Same thing happens if you look over at arrow B. Right? You've got what looks like a ring. You can't quite see the whole thing because it kind of trails off the edge of what I've cropped out for the map here, but it looks like it's basically a ring, and then you've got other concentric rings around it. So you're probably looking at a hilltop over there too. So as you look around this map, you can identify spots that look like hilltops because you've got a nice ring surrounded by other rings with these contour lines. Then you can see the valleys that are in between them. So the valleys will be these kind of crevices in between the hilltops. So if you look at arrows C and D, we're looking at a valley there. So there's a valley coming in between some of these hills. You can also see a nice example of a valley just north of arrow B. You can see there's the little gray road there. It's running up a valley because then there's another hilltop to the north of that, kind of just under where my face is on the video. So that's one thing that you can look for to just kind of get yourself oriented to the map. Second thing you can look for is water. Water always runs downhill. Right? That's a pretty basic thing, but it's a thing that you can use to help you get oriented to what's going on the map. Since water is going to run downhill, any water features, something like a stream or river, is probably going to be at a low spot compared to what's immediately to either side of it. So if you look at that little stream that runs through where C and D are, right, you can see there's a stream there. So that's probably the bottom of that valley. And then you've got the land going up to either side of where that stream is. So if you were to be standing in that stream and you were to walk perpendicular to it, so for example, at point D, you'd walk straight north or straight south, you'd be going away from the stream. And so you must be going uphill, right? Because the stream's going to be downhill from you. If you were going downhill there, the stream would have gone downhill with you. So if you're walking perpendicular away from the stream at D or C, you're going uphill away from where the water is. Then a third thing that you can look at is you can look at the actual numbers. So in this particular map, we've got numbers that are in feet above sea level. So again, USGS uses feet on their topo maps, I think just because they're meant for the public. Most people are more comfortable with feet. So these are in feet above sea level. And so you can look for contour lines that are close to each other and see which has a higher number on it. So just above point A there, you can see that thicker contour line is labeled 800. So that's 800 feet above sea level. Then a little north of that, you see a line that's labeled 700. A little north of that, one that's labeled 600, and then 500. So that tells you you're going downhill as you go from A down to the Lehigh River because the numbers are getting lower. You're going lower down in elevation. So that can also help you figure out where are the high areas, where are the low areas on this map. And I think that's a good starting point before you even start to answer whatever specific question you might be asked about the topo map, is just to kind of get it in your head, a sense of, okay, what are hills, what are valleys, where's the higher areas, where's the lower areas on this map. So then you might want to be finding out the exact elevation of a particular spot on the map. So say we're interested in the height of the top of that hill at A. So the first thing we want to do is find the nearest contour line that's actually labeled. So you'll see on this topo map, and this is very common on topographic maps, they're not labeling every single contour line. They're labeling ones every so often. We call these index contours because they have the number. They have the index on them to tell you what height they are. So we can see there's one very close to A that's labeled 800. So that line is 800 feet above sea level. If you were to walk around the circumference of Dieters Hill, staying exactly on that dark contour line there, you would not be going uphill, you would not be going downhill. You would be staying at exactly the same elevation, exactly 800 feet above sea level as you go around. Okay, so we know that's 800, but the top of the hill is not on the 800. The top of the hill is above it, and in fact, the top of the hill looks like there's another of the smaller contour lines before that. And that small one's not labeled, but we can figure out what elevation that small one represents. Because if you look where you've got the 800 and the 700 right next to each other, you can see that those are labeling the dark index contours, and then you can count the number of the thinner ones in between. And if you do that, you can see that there are 4 of those thinner contours in between. So that means the space between 700 and 800 is broken up into 5 steps, right? Those contours, 4 contours, break it into 5 steps, from 800 to the first one, to the second one, to the third one, to the fourth one, to the 700. And so that's a 100-foot elevation difference. You break it into 5 steps. Contour lines are always evenly spaced in elevation. So that means each time you hit one of those smaller contours, you've gone up or down by 20 feet. So if we were to put a label on that little ring right where A is, that would be 820. Right? So you've got the 800, you go up to the next small one, you're going up 20 feet, so that's 820. And then the peak of A, it's probably not, perfectly flat right at 820. It probably goes up a little more. So the peak of A is somewhere above 820, but it's not quite 840. Because if it went all the way up to 840, we'd get another ring. It would be high enough to have another contour. So the very peak of the hill at A is somewhere between 820 and 840 feet above sea level. Okay, so that's how you can figure out the exact elevation, or the elevation at least within a range based on the contours. If something were to be located exactly on a contour, then you could get the exact elevation. And you can do that not just with the top of the hill, with any point on the map. You take your point you're interested in, you figure out the nearest contour line that's labeled, and you count the smaller contour lines in between if necessary, and you can figure it out. So if, for example, we take a look at, let's look at the road intersection just southwest of A, where Dieters Hill Road meets, what's that, Nis Hollow Drive, coming around there. Right, so there's a little that intersection there. So that's downhill from A. So you can see it's below the 800, but it's not yet down to the next dark one that would be 700. So it's somewhere between 800 and 700. Then we can also see that we've gone down, we're going, like, imagine you're coming downhill from A, you've crossed the 800 contour, you cross that next small contour, that's going to be 20 feet lower, so that's going to be 780. And then you hit the intersection before you get to another contour line, which would be 760. So that intersection of Dieters Hill Road and Nis Hollow Drive is between 760 and 780 feet above sea level. Okay, so you can do that at any point on this map. You could figure out its elevation within a range of 20 feet based on what contour lines are nearby. Another thing you can do is you can figure out which slopes are steep and which are shallow. So if you look at point A, if you imagine going north towards the Lehigh River, you've got a lot of very closely spaced contour lines. So you're going to be crossing a lot of contour lines in a short period of forward distance. So that's a very steep slope. You've got a very steep hill down from Dieters Hill to the Lehigh River on that side. Right? You're going a big change in elevation over a very small horizontal distance. On the other hand, if you go south from the peak of Dieters Hill at A, you see that the contour lines are much more spaced out. Right? They're farther apart, so that means you're going forward quite a ways to hit each next contour. And so it's a shallow slope. You got a long horizontal distance to cross very many of those contour lines indicating changes in altitude. Okay, so the Hill A, Dieters Hill, is steeper on the north side than it is on the south side. One more thing to take note of that is good to be able to see on a contour map. You can see it really clearly if you look at point D there. As you look along that stream, right, the stream is at the lowest spot of its immediate surroundings, but the stream is still flowing downhill. That stream is going to be flowing down off of these hills into the Lehigh River. And so as it does that, you'll notice it keeps crossing contour lines because it's going downhill. But those contour lines, as the river is hitting them, are making these V shapes. And the V's are pointing upstream. So that's very characteristic. Whenever you see a stream valley, the contour lines are going to make a V shape as the stream crosses them, and the V's are pointing upstream. So that's a very helpful way if you're not sure which direction the stream is flowing in. You know, if I had cropped this so that we couldn't see the Lehigh River on there, which is kind of a giveaway because, you know, little streams tend to flow into big ones. But if you couldn't see that and you didn't have that indication, one way to very easily tell which direction that stream is flowing is to look for the contour lines as they cross the stream. They're going to form V's pointing upstream on that stream. So hopefully that gives you a good sense of some of the basics of how to read a topographic map. That's going to be a very important thing as we continue with our class, to be able to take a topographic map and understand what's going on in the landscape. Okay, so for the third section of our lecture, we're going to talk about GIS, Geographic Information Systems. So these are computer programs that allow us to analyze spatial data. So rather than just looking at a static map that's, whether it's on a piece of paper or, you know, a JPEG or something, a map that just sits there and shows you things, you can actually manipulate that spatial data. You can use it to answer questions. So in a GIS, you're going to combine usually multiple different variables. So multiple different things that you have data about for your area that you're interested in. And we call each of those variables a layer. So each data set that contains a certain variable of data is a layer. And this comes from the precursors to computerized GIS, when we would actually draw maps on clear plastic sheets, and we'd actually like literally stack them on top of each other so that we could add and subtract data. You know, we could take the streets off if we wanted to get a clearer look at something else and then put the streets back on. And we were literally stacking clear sheets of plastic. That was the state of the art just before I got my PhD. We had transitioned into computer-based GIS just in time that I never had to do that when I was studying. But we kept the kind of the metaphor that we're stacking these layers of data on top of each other. And so in the illustration, you can see kind of how that works. Right? So they've got, the real world's got all kinds of things going on in it, and they've got different variables about that. They've got the land use, they've got the elevation, they've got the parcels of land, like land ownership, they've got the streets, they've got where the customers of some business are located. Right? So each of those different variables is its own layer, and then you can stack them on top of them at each other and match them up based on where they are. Right? This is spatial data. You know where things are, and so you can use that to align these different layers and therefore ask questions that combine these different variables. And so to do this, we have some very powerful desktop applications. So programs that you can download to your computer if you want to do a lot of high-end analysis. So these would be things like ArcGIS, QGIS, IDTRICI. And if you're really interested in GIS, we've got some courses in my department, and you'll learn all about how to use these desktop applications to process geospatial data. And you can bring in some gigantic data files and do stuff with them when you're working on a desktop application. But there are also web-based applications. So there are GIS systems that you can access just through your computer browser. And these are going to be things like Google Maps, OpenStreetMap, Arc Online. And that's what we're going to be focusing on in this class. I'm not going to ask you to download a program to your computer. I don't want to deal with the headaches of troubleshooting all that on all your different computers that you might have. And it's just not necessary. We're not getting into it so deep that you need the processing power of QGIS to do the things we're doing for this class. But we're going to be looking at a lot of online systems that are able to do some of these basic functions. So we want you to be able to understand what can we do with GIS and how do we navigate a GIS system. So in your activity, you're going to get to navigate some GIS systems and learn the ins and outs of those things. So I'm not going to spend a lot of time on that here. Instead, I want to talk about what are some of the things you can do with GIS. Why would you turn to a GIS rather than just a static map or even non-spatial data? All right, what's the power of GIS adding to our analysis? So the most basic thing that GIS can do is it can make your map interactive. And there's kind of an irony here that I've got a screenshot of an interactive system here, so this is not actually interactive on the screen here, but if you were to go to the actual website that this came from, you could explore the interactivity of it. So this is a map of air quality based on smoke from wildfires. And so we've got all your data presented there as these points that are colored based on air quality. You've also got these areas that are in gray for smoke plumes. But if we were on the actual website that this came from, we could interact with it. We could zoom in and zoom out. Right? So in some of those areas, you see there's a lot of points piled close together. If you want to see exactly what's going on there, you can zoom in on them. You could zoom out to get the big picture. We could also click on individual ones. So if we clicked on something, we'd get exact data for it. So we wouldn't just have to say, oh, it's yellow, so it's within this range. We could click on it and get the exact information. This is a system that's updating constantly. So rather than being stuck with one map that was made at one point in time, they're constantly feeding new data into it. And sometimes you actually have access to the old data as well. So you could compare today with yesterday and flip back and forth between them and see if the air quality has gotten better or worse over that period of time. So we can just make our exploration of this spatial data much more interactive. That's the simplest, but also often a really important, powerful, useful application for GIS. Another thing we can do with GIS, if we think back to that idea of layers, is that we can overlap different data sets and look for correlations between them. Is this thing found in the same places as that thing? And on the basis of that, we can then draw conclusions about either the causes and or consequences of those interconnections. So here's an example from an online GIS system where I've got two layers here. One is the locations of hazardous waste sites. So these are sites that might be an environmental risk to people, right? You might be worried about the possibility of this, harming the health of the people that live nearby as they bring waste in and out of it and store it there, etc. And then I've overlapped that with data on the wealth of locations. So this is percentage of households with incomes above $200,000 a year. So this is basically showing us the darker blues are the richer areas, and then the greens and then light yellows are the poorer areas, right? So this is telling us about the income levels, the wealth of people in different places. So we've overlaid these so that we can ask, are hazardous waste sites usually found in poor neighborhoods, usually found in rich neighborhoods, or is there no relationship? They could be equally found anywhere. And in this case, just by looking at this map, you can probably already get a sense that hazardous waste sites tend to be located in poorer areas. Right? The poor areas are much more likely to have a hazardous waste site in them than the rich areas, at least what it looks like from looking at it. Right? So we can just get that visual on it, but then, and that's all the online system can do, is give you the visual on it. But if we pull this data into a desktop application that can do a lot more stuff, we can actually run some statistics. Right? We can do some math to determine, is that relationship real? right? We can see if that correlation is actually statistically valid. And in this case, if you do that, and lots of people have done this, and we find that that correlation is actually statistically valid, that there is a correlation that poor people are more likely to be living next to a hazardous waste site than rich people throughout the United States, as well as in particular locations like this you may have recognized from the shapes of things is the city of Pittsburgh here. So we can overlap different kinds of data and we can examine whether there are correlations between them. Now, correlation doesn't tell us causation, right? Why do poor people tend to live next to hazardous waste sites? That we would need additional information to answer. And what are the consequences of it? We'd have to dig farther to examine that, but we at least get that starting point to say, yes, there is a connection, that these two things are found together. They're not just randomly distributed. So we can look at these overlaps and correlations. Another thing we can do with GIS is wayfinding. We can find a route from one place to another. What is the easiest way to get from point A to point B? And this is a function you've probably used a million times in your life without even thinking about it. It's the most common thing you do with, say, Google Maps or Apple Maps or Waze or whatever other app that you might use to get around. And here, just for fun, I plotted out the best way to walk from my home in Avalon, Pennsylvania, up to Slippery Rock. It looks like it's going to take almost 16 hours of straight walking, so I should probably commute by car rather than by foot to get to class. But it has analyzed the connections of all the roads, what kind of speeds you could get on different roads, and found me the best path through that landscape from point A to point B. So that's a wayfinding function. You can also use GIS to optimize things. If you have several different variables and you're trying to balance them, you can feed them into a GIS that will combine them to figure out where the optimal balance is located. So this comes from a study of grazing productivity in Australia. So what you're seeing here is data for areas of Australia that are rangelands, so they're cutting out like forest areas and the desert areas that have nothing growing in them. But then they're combining a whole bunch of different variables, a whole bunch of different things that are relevant to whether a spot is going to be good for grazing cattle and sheep. So they're looking at things like the soil composition. So across the top right there, you see things like soil carbon, soil nitrogen, soil phosphorus, right? Those are different variables, and you want to try to find the best balance of all those. You want to find a spot that's got, maybe not the most nitrogen, but it's got lots of phosphorus too, as opposed to, say, a place that has tons of nitrogen and no phosphorus. That wouldn't be good. You need both of those to grow the grass that your sheep are going to eat, right? And then you've got rainfall on there as well, right? You need rainfall to grow the grass for your sheep to eat. So we can combine all these different variables that affect whether an area is going to be good for sheep grazing into that final largest map that is our overall productivity potential. So that's identifying the best areas for grazing. So we can combine all these different variables to find out what's the optimal place to do something. And all kinds of uses of this go on all the time. Anytime you see a new, say, dollar store opening up, they've probably been feeding a bunch of variables into GIS to figure out what's the optimal place to build our next Dollar General, based on all the variables that they think will go into making a successful store. And then it spits out, here's your optimal locations, and then they pick what they think the best one is and go buy the land and build a store. So there are all kinds of applications you can have for this kind of process that you can do through GIS. And then the last and kind of most complicated thing you can do is modeling. So if you have a process that you're interested in that operates over space, and you have an explanation, a theory as to how it works, you can build a computer model using GIS that will run through that process to predict what would happen. And then you can first run the model and compare it to actual data to see if your theory is right. Is your model producing something that looks like what really happened? That's an indication that you've got the right idea, that you've got the right explanation for what's going on. And then you could run your model into the future to try to predict what's going to happen in the future under the prevailing conditions. So this is an example of predicting Amazon deforestation. So they built a model based on their theory as to what kind of things cause deforestation. And there are a bunch of different variables that went into that, right? There are a bunch of different things that might make one area more or less likely to be deforested. So for example, areas that have good soil for growing crops are more likely to be deforested because somebody's going to want to cut down the rainforest and plant a soybean field there. Areas that are close to roads are more likely to be deforested because it's just easier for people to get to that spot and bring their equipment in and deforest it. So you put all these different variables together, you have a model of how they interact with each other. You can run that model based on past data to see if you can accurately predict the present. And if you can do that, then that validates your model and you can use it to predict what's going to happen in the future. And you're making spatial predictions when you're doing this in GIS. So the results from this particular study were predicting 10 years out. So this is a study published in 2020. So they predicted 10 years out, so 2030, and then 30 years out, 2050, what areas would become deforested. That's what you see in the lower two maps there. The red areas, the areas that their model predicts are going to be deforested. And so we could then take that and use that, if we're worried about deforestation, we think that it's a problem, we could focus on protecting those areas or enforcing laws against illegal deforestation in those areas. It would help us target that rather than trying to equally protect the entire Amazon when some areas might not be threatened by deforestation, at least within a certain time frame. So our GIS can also allow us to model what is going to happen and use that to check our explanations of things. Okay, so hopefully that gives you a good idea of how maps work, how GIS works, and gives you a good starting point for working on your activity for this week's class. And I will see you next time.